Nowadays, lithium-ion batteries are most commonly used rather than alkaline or lead-acid batteries. The ability to recharge a battery back up to full power is what makes these batteries so great. Lithium-ion batteries have many advantages from using them, and are most commonly used to power our phones, laptops, tablets, and let's not forget about electric-powered cars. Why lithium? Well, because lithium is the lightest of all metals, has the greatest electrochemical potential, and provides the largest specific energy per weight. Rechargeable batteries with lithium metal on the anode could provide extraordinary high energy densities. In this video, I'm going to be explaining the physics side as well as the chemistry side when lithium-ion batteries are put to use. What we just saw right now was a lithium-ion battery being used by an electric car. Before we get started, I want to explain the basics of batteries and how they work. So it's really quite simple. All you want to do is transfer electrons. So what you have is a cathode, which is a positive plate, and what it does is it wants electrons, so it's lacking electrons. Then you have an anode on the other end of the battery, and that's a negative plate, so it wants to get rid of electrons because it has too many of them. Then in the center you have an electrolyte, and what an electrolyte does is that it prevents the electrons from the anode from simply going over to the cathode. So it's a separator between the anode and the cathode. So when you connect a coil or wire between the two ends of the battery, you allow the transfer of electrons to occur. So the electrons will leave the anode and travel to the cathode, since the charge of the battery is negative. Anode and cathode materials are chosen specifically so that the anode donates electrons and the cathode accepts them. The tendency of a material to donate or accept electrons is expressed as the object's standard electrode potential. The difference between the electrode potentials of the cathode and anode determines the voltage of the entire cell. So again, to recap, the anode and the cathode are separated by the electrolyte, which is a liquid or a gel that conducts electricity. When the anode and cathode are then connected to each other through a wire, the anode undergoes a chemical reaction with the electrolyte in which it loses electrons, creating cations or positive ions, a process called oxidation. The electrons and cations meet at the cathode where they undergo a chemical reaction called reduction. Together, the entire process is known as reduction oxidation or redox reaction. The electrons travel through the wire from anode to cathode because they are at a higher energy in the anode than in the cathode. Chemical reactions in the battery can last for some time, but not forever. Eventually they deplete or corrode the anode and cathode, leaving insufficient material to keep the reactions going. In a lithium-ion battery, the lithium ion is the cation that travels from anode to cathode. The electrolyte is typically a combination of lithium salts, such as lithium hexafluorophosphate, lithium tetrafluoroborate, or lithium perchlorate, in an organic solvent. Graphite carbon is most commonly used for the anode, and lithium cobalt oxide is most common cathode material. The combination gives an overall voltage of 3.6 volts, more than twice that of a standard AA alkaline battery. That gives lithium-ion batteries a much better energy per volume ratio, or energy density, than an ordinary alkaline battery or other common rechargeable battery. This is because lithium is the third smallest element after hydrogen and helium, and thus a lithium ion can carry a positive charge in a very small amount of space. Increasing the amount of energy that can be put into a given volume of battery is one of the major challenges facing battery makers today. This is something to look into. Lithium-ion batteries, unlike standard AA and AAA alkaline batteries, can be recharged by running the anode and cathode reactions in reverse. This is usually done by a charger that is plugged into a powerful electricity source such as a wall socket. The ability to be recharged many times over without much loss of capacity is another major advantage of the lithium-ion battery. Lithium-ion batteries are not perfect. The amount of charge your cell phone and laptop batteries can hold decreases after a few years. Lithium-ion batteries develop increased internal resistance over time, which decreases their ability to deliver current. In addition, lithium-ion batteries are vulnerable to a number of potential problems. These include overheating at the anode and oxygen production due to overheating at the cathode. These two problems together can cause a fire. Today, lithium-ion batteries are manufactured with protections to limit the charging voltage and to shut off the battery if the temperature becomes too high. This protective precautions and circuitry does make the battery safe, but it also reduces the fraction of the battery that is used to store energy, and also slowly drains the battery even when the device is off. Battery makers are constantly trying to improve these safety features and increase the capacity of the batteries. The future looks bright for this hard-working battery to appear in more devices. Much of the recent efforts to improve the lithium-ion batteries have focused on developing anode and cathode materials that can hold more charge in a given volume, leading to higher energy densities. Many research groups are focusing on replacing the graphite anode with silicon, which could potentially store up to 10 times the current capacity. The downside is that silicon films tend to expand when absorbing lithium ions during charging, and shrink again when releasing lithium ions during discharge, leading to pulverization and fracturing the anode and a short life for the battery. But recently, a group led by this man of Stanford University has used silicon nanowires to create an anode that does not have this weakness. Another idea that has attracted a lot of attention is using lithium iron phosphate for the cathode. While it has slightly a lower capacity and much lower conductivity compared to lithium cobalt oxide, iron phosphate is both cheaper and less chemically reactive. Some tips for extending lithium-ion battery life is to keep them at room temperature, and to also avoid completely discharging them. For extended storage, you should discharge them to about 40% and then store them in a cool place like a refrigerator. But don't store them somewhere like in a freezer, that's too cold. Hopefully, in the near future, lithium-ion batteries will continue to improve and have a positive impact on society.